Hello my dear friends, in the last video we have learned a basic definitions of thermal analysis. Now we'll derive the differential equation for one-dimensional heat conduction. Differential equation for an one-dimensional heat conduction.
To get this differential equation for a one-dimensional heat conduction, we'll consider a heat conduction across the wall thickness through unit area of cross section with uniform heat generation as shown in figure along x direction only, and a insulating boundary along y and z direction. We'll consider a parallelopiper. Here you can see heat flow will takes place along x direction when the heat is enters to this wall in this particular surface and exit from this surface of a parallelopiper along x direction. Heat enters to the wall is said to be as a q of x. Heat exit by the wall is q of x plus dx, which is representing as a qx plus dou qx by dou x into dx. This is the x direction and this is z direction, this is the y direction. Z direction and y direction is insulated here. You can see is insulated z and y. Only the heat flow will takes place along x direction with respect to this surface area. The surface area is acquired to heat flow along x direction is depends upon the dz and dy. The area of cross section A is equals to, with respect to heat flow along x direction, dz and dy. See here, as per this along x direction only the heat flow will takes place insulated boundary along y and z direction. Now we know that energy balance equation under the steady state condition, heat inflow plus heat generated is equals to heat outflow plus change in internal energy. This is a law of conservation of energy equation, which is energy balancing equation. We are well known, where q of x is in a heat enter in the wall, q of x plus dx is heat leaving the wall. We have that q of x plus dx is equals to q of x plus dou qx by dou x within the dx value. Then rate of heat generated per unit volume, this is the volume what we have shown in the figure. A rate of heat generated per unit volume, that is equals to q of a into dx, where we are considering a flow of heat along x direction. Heat is entered q of x and leaving q of x plus dx, that acquires the area which is d z and dy, that area of cross section. Flow of a heat will takes place along x direction, that is dx. Heat is generated throughout the volume q is equals to a into dx, but it is not transferring along y and z direction, it is move only along x direction. When the heat is generated by the system is said to be as a positive, heat is consumed by the system is said to be as a negative. Then this equation is under equilibrium condition. Input flow, that is entering the heat to the system with respect to the area of cross section A, is said to be as a heat inflow. Then q of x into a is rate of heat flow into the system, plus of heat generated by the system q of a into dx is equals to heat outflow, where heat outflow, which is equals to q of x plus dx, is equals to q of x plus dou qx divided by dou x into dx. This q of x plus dou q x divided by dou x dx I have taken directly instead of taking this value into a, is said to be as a heat outflow with respect to this cross section. Then change in internal energy of the system is considered as a zero. Why? It has been insulated, only one directional flow will takes place. Now rearrange this equation, q of xa plus capital Q A into dx heat generated by the system. I'll take common on the left hand side. Q of x plus Q into dx remains into A, and then we have A outside. Directly we have copied again this one, then rearrange this equation, cancel that left hand side and right hand side value. So a will get cancelled. After cancelling that a remains q of x here in the both side. Q of x will get cancelled. Then q into dx on the left hand side is taken, remaining value dou q x by dou x into dx. Then dx will get cancelled, only remaining a q into dou qx divided by dou x. Call it as equation number 1. We need to find out this q of x. Will get the differential equation of equilibrium for the given condition. Then that q of x is nothing but a heat flux. As we know that from a 4-year law of conduction, within a body the conduction heat transfer will take place, where the heat flux q of x is equals to minus of k into dou t by dou x. This is a conduction heat transfer rate of equation. Then this value will substitute in the equation number 1. In the equation number 1 we get q is equals to dou by dou x. Q value becomes minus of a k dou t by dou x. Then we have a q is equals to, rearrange this minus sign outside, we have taken minus of dou by dou x into k into dou t by dou x. Then rearrange this equation, just you take down this left hand side and dou by dou x k dou t by dou x plus q is equals to 0. Call it as equation number 2. This equation number 2 is said to be as a governing differential equation for one dimensional heat conduction.